How's it going? We are the Solar Optimized Land Autonomous Recharge and Intelligence System, SOLARIS. We are a group of 4 senior engineering students who attend the University of Central Florida, a mix of electrical and computer engineers. Our software lead is Ryan Markowitz, a computer engineer. Our power lead is Raphael Puig, an electrical engineer. Our PCB lead is Nathan Hammond, an electrical engineer. And our hardware software integration lead is Garrett Fortier, a computer engineer. Our engineering specifications cover many different requirements for Solaris' success, some of them being robot speed, dimension size, solar panel tilt and rotation degrees, weight, solar panel power output, Bluetooth low energy range, ultrasonic sensor range, and even energy monitor accuracy. When checking our motherboard, we found errors with our programming circuit, and as a result, had to jump our TX and RX lines on our first revision. This video here shows us finally getting our first line of code programmed to our ESP32 unit on our motherboard PCB. We made sure that our phototransistor PCBs functioned correctly, and that we could see the full load voltage fed through when light was applied to the phototransistor.
Here we are validating the I2C interface for the IMU. To improve signal integrity, we added series terminating resistors on the SDA and SCL lines to reduce ringing and improve communication reliability. We then verified stable communication with the sensor and confirmed consistent transmission before integrating the IMU into the robot. Here, we are validating that our ultrasonic sensors work in the lab before integrating them into the robot. The 4-to-1 multiplexer we use allowed the microcontroller to switch between multiple sensors while minimizing the number of required inputs. We confirmed that each sensor was selected correctly and produced the reliable distance measurements based on our calculations.
When initially testing our motor drivers, we ran into a little bit of trouble. We realized that one of our components was wired incorrectly, and therefore directional pins used to control the direction of the motors had to be hot wired for testing. However, the demo shown is a show of success and allowed us to redesign the PCB and order a new one as our first revision. To test the current draw for our motor under a load, we tied the motor to a weighted box and pulled and watched the current to make sure there was no unnecessary spikes. To integrate the motors into the system, we decided to mount all 4 of the drive motors onto the chassis to test them for forward and backwards motion. The motors would run in a forward motion for 5 seconds, accelerating up to top speed, and then decelerating after 5 seconds. And then they would go backwards, accelerating and then decelerating over the same 5-second period.
This is an overview of the subsystems in Solaris. At this stage of the project lifecycle, our team has achieved successful milestone completions regarding the preliminary fabrication, assembly, and bench testing of several critical breakout modules: the voltage regulator, motor driver, energy monitor, phototransistor system, and motherboard. We are in the process of receiving a reworked motor driver and motherboard after initial testings of these PCBs gave us insight on issues with the design. Velocity validation testing was performed to verify the robot's 0.3 meters per second speed requirement. Across 10 distinct trials over a controlled 128-inch course, the robot achieved an average travel time of 8.28 seconds, translating to a forward velocity of 0.39 meters per second. This performance surpasses the baseline requirement by 30%, Because the drivetrain utilizes bidirectional motors, reverse speed characteristics are expected to mirror these forward velocity results. Physical specifications of the robot, Solaris was built with a final footprint of 19 by 24 inches, and it stands at 29 inches tall. When fully assembled with all its components and subsystems on board, the total mass is estimated to come out to around 36.41 pounds.
To test our energy monitor for correctness, we decided to hook it up with a test load, and then from there, we would read the current out from the DC power supply and verify it on the terminal, which was being read over I²C from the actual energy monitor unit. As you can see on the left, as the log scrolls, the current is updating as well as the bus voltage, both within 99% accuracy, which meets our specifications. For our pan and tilt motors, we wanted to verify that we had no mechanical constraints for our full range of motion required by our specifications. 30 degrees on the tilt axis and 360 degrees of motion on the panning. As you can see in the demo, we tested the motors to see if there was any obstruction that would stop them from rotating freely.
So this is the phone app side of Solaris. When you open the app, you land on the home page, and then you sign in. Once you are signed in, the phone app will attempt to connect to Solaris via BLE. As soon as the connection is up, the app will do two things. It pushes the current time down to the ESP so its logs get timestamped correctly, and it pulls weather information from our backend API for things such as cloud coverage percentage and precipitation percent chance. Solaris uses that to make a more informed decision on whether it should move out of shade while it's in the autonomous mode. After that, the app asks the ESP for telemetry. Solaris has been writing log entries to Flash throughout the day, so there's usually a chunk of data waiting. We move it over with a small ACK-based protocol. The app kicks off the request, the ESP sends one page of logs and waits for an ACK before sending the next. If the resend timer fires before an ACK shows up, it sends the same page again. Once the final ACK lands, the ESP knows everything is safely in our database, and it wipes its local logs. From there, you are greeted with a telemetry page. That screen pulls from our Fast API backend, which reads everything out of our Postgres database. That data shows up as swipeable cards, such as battery percentage, CPU temperature, distance traveled, and net power gained. The first page of each card is the most recent reading, and as you swipe sideways, you get bar graphs going back 24 hours, then a week, then a month. The last screen is mode change. There are three options: stationary, automatic, and manual. Stationary keeps the robot put. Automatic lets Solaris run on its own and reposition out of shade when it detects that it needs to do so. Manual hands control over to the user, and the app starts streaming steering and throttle commands to the ESP over Bluetooth. And that concludes the app.
Moving forward, we are soon to receive two new revisions, one for our motherboard and the other for our motor driver board. We plan to continue integrating all our systems to one big cohesive system. Thank you.